We're looking at Unit 2. Unit 2 is going to cover the Sun and our solar system. So we'll start with the closest star to us, Sol, the Sun, and we'll look at its structure. And again, this is based on the Standard Gravitational Model that assumes that the Sun is a ball of nuclear fission elements. Throughout most of history, we used to believe that the Sun's energy came from fire. Actually, it was relatively recently, in the last 100 years or so, we started deciding it was something different. And we knew from our own personal experience, things that burned produced heat and light, and the Sun definitely produced heat and light. So they didn't link these two forms of energy to a third and fourth, which they're also familiar with, mechanical or motion, and plasma or lightning. So they knew about things moving, they knew about lightning. They might not have called it mechanical or plasma, but they didn't put these four forms of energy together. So you're looking at heat, light, motion, mechanical motion, plasma. And I have one of these little puppies here. So when we get back into school in another week or two, we can play with it. From a spectroscopic analysis, in other words, using the spectral, which we're looking at bright line and dark line, mostly in dark line analysis, we have detected up to 67 of the 92 naturally occurring elements in the Sun. Previously we talked about 91, but there are now 92 through lead. The top 10 known natural elements that we have detected in our Sun are hydrogen at a vast majority at 91.2%, helium in a second place at 8.7%. Then as you see, it's just fractional percentages, but there is oxygen on the Sun, carbon, iron, sulfur, nitrogen, silicon, magnesium, and neon gas, believe it or not. So they do exist in the element form on the Sun. And these are their spectral lines. These are bright line spectra here, which identify it. And this is the dark line spectra. Thermomagnetic analysis was also indicated that from the heat and from the magnetic field, it indicates that there are three basic regions in the Sun's overall structure. We have the center of the core, then the inner zones, and then it has an atmosphere. The last two actually have smaller division or layers within them as well, each with their specific characteristic. And so kind of like color wavelengths in the visible light spectrum, these layers are not distinct. You just don't have the hard edge like drawn by the artist. One tends to blend into the other as you move through the layers. So as I move through, I went from the core to the inner zone to the atmosphere. The core, also known as the center, has a diameter of about 1.3 million kilometers and operates estimated at 15 million degrees Celsius. There are no liquid solid forms of matter can exist, only the gas state can. We know from energy diagrams, if you have in chemistry, that we're way off the phase diagrams. When you have that much pressure and that much heat, you can't stay in the two lower states. It exists as a gas, or we get to plasma. So you're looking at a core about 15 million Celsius. And it makes up about 10% of the overall diameter. So it's about a tenth of the way across from what it is all the way through. And it's comprised almost entirely of matter in the gaseous state, and it has a very high density, about 10 times greater than iron itself, because it's compressed so tight together at about 80 grams per cubic centimeter, where iron runs about 7.96. So it's about 1/10 the distance. If you look at iron, this is even much more dense, 10 times. So you took that and squeezed it down by a factor of 10. You got an idea. Inside the cores, the atoms are stripped of their electrons, leaving only the centers or the nuclei. And that's, again, due to this immense pressure and heat. And because they're pressed so close together, these nuclei will fuse or join together, which creates nuclear reactions. And so you go from smaller to larger atomic nuclei. And we've touched on this already before in the last unit. This is an actual photograph, time-lapse photography of atoms undergoing nuclear reaction within a reaction chamber. From fusion, we talked about before, it's two forms, isotopic forms of hydrogen, deuterium and tritium. So they're both hydrogen. They both have one proton in the middle, which defines them as hydrogen. But this particular form has two, means like dual. One of it is a proton, one is a neutron. Where this one, tri or three, again, one proton, which defines as hydrogen, plus two neutrons. So when they fuse together, the two protons become two. Well, anytime you change the number of protons, if you know from chemistry, you change the element. So one is hydrogen. When I have two in the middle, two protons in the middle, I now have helium. Of the five neutrons, four of them retained with the helium, and one of them gets kicked out. So we actually have one neutron that'll actually come flying off after this reaction, and a lot of energy. So as the two get together, they fuse to form helium, and the one neutron, along with a huge energy release, 3.5 meg of electron volt, is basically what 26 people would use in the course of a year. There are other theoretical nuclear fission process pathways, which have been demonstrated on a lab scale, but when they try to scale it up to a large scale process for the natural situation of the sun's actual core, one of these processes is actually a 5-step process known as a proton-proton collision fusion. So I'm just looking at the protons in the hydrogen. In that case, we're saying they have two protons that join together. What will happen is a proton, if it picks up an electron, becomes a neutron. So in which case, we're getting this process here. That's gamma radiation. It's a high energy radiation. You get two of these going together, you now have helium. In this case, you kick out two protons. So it starts off with two hydrogen protons with no electrons. You kick out a beta electron and a regular electron. You become deuterium. Another proton will hit. I now have helium, but it's short a neutron. Two helium nuclei will fuse. And now I have a full-fledged helium, which kicks out the two protons, which degrade. So that is a proton, and we show it down here. Hydrogens forming helium with this little beta radiation that comes out and gamma radiation. There's another way they show it here with the 4 hydrogen forming helium. And because two of the protons turn into neutrons, we kick out these little particles called neutrinos. Those stream through everything. And some of the actual experiments we have with old salt mines full of water will show that. Regardless of which pathway, the end result is helium, which has a mass about 70% less when you combine all the hydrogen isotopic forms needed to form it. So it loses some of its mass. And that's where the little neutrinos and energy come in. And it's due to conversion of mass to energy. That's Einstein's favorite little formula we all know about. Energy equals mass times the speed of light squared. So energy and mass, if they're equal, to make this thing come out equal, I got to multiply this by a really big number. 300,000 squared of these mass units will equal 1 energy unit. And this is actually some of that energy release that you see with the particles on the sun's surface. At this rate, how many tons of hydrogen are converted per day? So we have this hydrogen gas, the small, so how much? Basically, this is the conversion that we do, 600 million tons per second. Almost 52 million tons of hydrogen are consumed every day for one of our days. This is 1 ton. This shell from World War I gives you an idea what 1 ton is. So think of 52 million of these. that would be the equivalent of hydrogen, light hydrogen being consumed. And we also have, as we talked about before, the heliums can join together. You got hydrogen, hydrogen goes to helium, helium, that goes to lithium, lithium, that goes to carbon, carbon, nitrogen, nitrogen, oxygen, oxygen. So these are also on the surface, we know from spectral analysis. They also fuse. And that's the end of this first section on structure.